Yeah, hello everyone. My name is Taejun Kim, and I'm from Music and Audio Computing Lab, KAIST, which is located at Korea. And it's really honored to be here in front of you DSP masters. And yeah, so this research is about DJing, and no many researchers are super serious about DJing. So probably you are not familiar with AI DJ or automatic DJ performance analysis. And this is about automatic DJ performance analysis. So I will go many background. So this presentation is quite introductory, so please understand. Yeah. Okay, so let me begin with the research question. So how do DJs control DJ mixers? So if you practice guitars, probably you will watch a lot of favorite guitarist video, and you will watch their hands very carefully like this. What's going on there? Like that? Yeah, actually, baby DJs are the same. They watch DJ videos, and they just want to know what kind of magic is going on their hands. So it will be very nice if we can automatically extract the gains or how do they're controlling, and etc., etc. So we proposed the task. We call it DJ mixing estimation. So it's simple. Given a DJ mix and tracks played in that mix, models should explain how the DJ performed mixing. So the explanation can be like which DJ mixer is used, or which audio effects are used, and how did the DJ control the audio effects, something like that. So, yeah, and we can use it for DJ education and hopefully for training data for AI DJ. But in this paper, we're not gonna tackle the first two type of question, but we will tackle time-varying gains of faders and EQs. It's actually very simple. It just looks like this. So if you put the original DJ mix and previous track and next track, then you will get this beautiful gain curve. So for example, this white line is fader gain. So for the next track, it was small, but it's being increased. That was the example. But actually, it has a limitation, and if you are DSP lover, you maybe think it's completely insane, because we just assumed DJ mixers have same model, which means same EQ, frequency cutoffs, and Q values, and so on. Yeah. All right, so let me tell you how we did it. First, we need DJ mixes, real DJ mixes. So we collected DJ mix dataset from mixesdb.com, and it's publicly available. I'm so happy because dataset is very rare in MIR community or DSP community. So, of course, but it doesn't have audio file itself because the license issue, but it contains metadata, and I also included the download code. So it has 5,000 DJ mixes and 63 tracks, only metadata. And most importantly, you can get which tracks are played in which mixes. So for example, in mix 1, 2, 3, 4, they played this kind of tracks, and they have links to audio. And you can install it via PIP. PIP install DJ mix. Pretty cool, right? And if you import the DJ mix, and if you call download function, it will download audio files. Yeah. But even though we get those DJ mixes and tracks, we need pre-processing. Because if you want to compare the signal from DJ mix and track, you need to align them precisely, right? And DJs usually change BPMs of tracks when they play music. So their BPMs and bits are not aligned. It's not enough that you find offset of track. So this is our previous work. So we call it mix-to-track alignment. So in this graphical view, so DJ mix has different BPM, but through our algorithm, track bits are aligned to DJ mix bits. And I'm not going into details, but it's basically based on bit tracking and DTW on spectral features. And after the alignment, to analyze the performance, we perform timescale modification on tracks so that their bits are aligned precisely. Yeah. Then after that, we can detect transition regions where tracks are moved on from previous one to next track. Yeah. Then now we can think about which gain should we apply to the original tracks to get the DJ mix. Yeah, we can simply think, okay, we should optimize so that their spectrogram look similar. But if you do without constraints, it goes crazy like this, because without constraint, it will generate very robotic values. So error is perfect, but it doesn't make sense. So again, in our previous work, we proposed like constraint, fade in, fade out constraint. So previous track should always fade out, and next track should always fade in. So their gain should be decreased like that, and the next track gain should be always increased like this. And if you use convex optimization, you can give strong constraints to them. So we applied convex optimization. Yeah, but our previous work has limitation that it can only estimate 3 EQs without faders, because if you include that fader and EQ, it's not a convex form, so it's unable to optimize. So, and actually, I didn't know where about DSP at that point, so it doesn't make sense in terms of DSP. So I studied DSP, but still I don't know much. So finally, now in this paper section, so in this paper, we designed optimizable DJ mixer. So this is naive DJ mixer design. So there are just 3 EQs and 1 fader. But actually, you cannot apply convex optimization to it, because if we use biquad filter to the EQs, it's really complicated. So it's not a convex form. And also, in convex world, you cannot multiply 2 variables. So we propose technique to make it optimizable in 3 steps. So I'm gonna explain the 3 steps. First, if we compute loss for each subband, low, mid, and high, we can only consider single EQ at once. Meaning, like this, if you compute loss for low subband, then it goes like this, and then if it's mid band and high band. Yeah. After that, we did linear approximation of EQs. So it's simply a box here right now, but actually a lot of things are going on there. So variables are on the top and bottom, but we made it simple like this. So yellow ones are constant, and cyan color is variable, and this purple one is also variable. But while doing linear approximation, there are gaps like this. So this black curve is actual biquad frequency response, but this purple one is the approximated one. You can see the gaps there, so it's not perfect. But you can make it linear. But still, you can see that the multiplication of variables, so if we substitute substitute those variables, finally, we get the optimizable DJ mixer. Yeah, so it's optimizable. And if you run that, you can get these beautiful curves. So now, okay, we got those beautiful curves, then how do we trust them? Because in the data set, we have DJ mixes, but we don't have ground truth gain curves. We don't know how did they control the gain knobs. But actually, we have some kind of ground truth because we have DJ mixes. So we decided to compare their spectrograms. I mean, like this. So using those extracted curves, we reproduce mix here, and using those error between the DJ mix and reproduced mix, we evaluate it. So this is the result table. So we tested on 2 different spectrogram inputs, which are CQT and MER spectrogram. And also, to be fair, we evaluated on both of spectrogram types, and also for each subband and also entire band, because it can estimate fade aware, but completely bad at low EQ, for example. And this is a baseline, just playing 2 tracks together, and this is simple crossfading from one to another. And yeah, and amazingly, there's a previous work other than us. So on the top, this is another work, which is not us. So it only used single fader and perform convex optimization on it. And this is our previous work I mentioned, and this is this work, but only with EQ3, and this is the our main proposed method. So it has, generally, it has lowest error in all metrics, except 2 metrics. So yeah, it's nice. But you know, it's just numbers, so I prepared the demo. So it's 2 minutes long, but it's so long, so I just play this short region. So previous track gain is decreasing, and the next track is coming suddenly. So the white one is fader, and the cyan is low EQ. Let me play. So first, the original DJ mix. Oh, sorry. This is the original DJ mix. And now the reproduced one. And only the previous track. The vocal is on the next track, so. Okay, now the next track. And reproduce mix again. And the DJ mix. So if you think they sound similar, it's successful, and please imagine if you can see this curve, and at the same time, if you can listen to the single track for each, then it'll be very nice for DJ education. Yeah. Okay, thank you.
Thank you for the super interesting presentation. I was wondering about about the crossfader curves. Maybe I missed the information that you gave, but in your previous work, and the question is if you did the same in this work, right? You used linear crossfader curves to estimate the crossfader level. You assume it's just a linear crossfader, right?
Not completely linear. I think I should say monotonically decreasing and monotonically increasing. So it looks like.
Right. So I saw that the result is not a straight linear curve. But I was wondering, you mentioned in the beginning that you assume that all mixers are the same.
Yeah.
And from experience, mixers, you can actually switch the crossfader curve from a linear curve to something that is non-linear. What do you first have you considered including the type of information that you find in the crossfader there in your work?
Type of curve.
The type of crossfader curve that is applied.
Type of crossfader.
You have a switch in some mixers that make, instead of a linear, non-linear type of curve that is applied.
Actually, I tried, but it didn't optimize well. So this was the first study.
Okay, so it might be interesting to also include, if possible, right? If you have more information about the model of the mixer and the type of curve that was used for the crossfader.
Yeah, actually, we are trying to move on using neural network and again DTSP. Yeah, so actually we choose convex optimization for constraints, but I think we can give regularization term to loss using DTSP and neural network. So I hope we can consider the types of mixing in the future work.
Yeah, well, there's a lot to be done. It's very interesting. Thank you.
Thank you.
All right, let's move on. Let's thank a speaker once again. Thank you very much.
Thank you.